Hey everyone, so what we want to do here is do some examples for drawing your forces, drawing your free body diagrams, and determining if an object is accelerating or not. And if it is accelerating, then knowing how to solve for that acceleration. In this example, this looks just like the one we did in class today with the stoplights suspended by two ropes. Actually, it is identical to the problem we did today. I'm going to change up one thing here and solve it slightly different. I'm going to make a rope T1 go right here. So the new scenario is rope down like this, T2, rope over this way, T1, and the stoplight hanging below it. So that's going to be my scenario. I'd like to run through how to solve this one with you and show you how we can find the forces. All right, so a good way to start any of these problems is to write your list of forces that are on the object and see which direction they're going in. We've got an X direction, a Y direction. Yes, there's a Z direction, but let's just try to keep it simple with two directions right now. All those forces must sum to the net force, and the net force must always equal MA. However, in this scenario, you've got the force of gravity acting straight down. You've got T1 acting to the right, and you've got T2 at this angle. So T2 is at an angle of 60 degrees from the horizontal. So when you go through your list here, you want to think about what forces are in which direction. So looking at my list, T1 looks like it's to the positive X direction. Nothing in the Y. T2, a little more complicated. I'll come back to that. But force of gravity should be an easy one. There's no gravity in the X direction, and it's minus mg in the Y direction. T2 is at an angle. So what we want to do, like we said before, is break this into its components. Get the two pieces here, get the Y component and the X component, and put those into your chart. Tx becomes negative T2 cosine, and Ty becomes T2 sine. And just like I said before, be careful with your sine and cosine. Make sure you know which side you're looking at. The Y is opposite the angle, and the X is adjacent to the angle. So that's how I know I can use cosine and sine. But it may not always end up that way. Just look at your angle and look at the legs and the components that you have. In this scenario, the traffic light was sitting still. So the nice thing about that, if it's sitting still, the two components down here for MA are going to sum to 0. There's going to be no acceleration in the X direction or the Y direction. So I can go and write equations for the X and Y directions here. In the X, I just go down the X column, go down this column, and add up everything and make sure it equals 0. So T1, so that tells me there, if T1 minus T2 cosine equals 0, actually that tells me T1 and T2 cosine must equal each other. So it's kind of nice. If I can find T2, I'm going to be good to solve for whatever T1 is, because I just have to take the cosine of T2. Let's look at the Y direction. The Y direction forces are T2 sine of theta minus mg, all adds up to 0. So again, what this is showing me in the Y direction is that T2 sine is just equal to mg, which is whatever the weight of my object is. So it's kind of nice. What I can say is, let's give it a mass, 20 kilograms. So let's use gravity as 10 to make the numbers nice and easy for us. I can say that T2 sine of theta must be equal to mg. That's mass times the gravitational field strength of Earth, which is around 9.8 or 10. So that means that this equals 200 newtons. If I want to solve for T2, T2 is just going to be 200 divided by the sine 60 degrees. So punching that in your calculator, you will get T2 to equal 230.9 newtons. And remember, we are in physics class, so make sure your calculators are in degrees when you're doing your trig. Not radians, we're not there yet. So knowing T2 is 230, I can put that into here, and T1 becomes, so just from doing some vector addition here, I'm able to calculate these two components based on organizing my forces into a chart and making sure they add up to 0. But this won't be the case in every single scenario. Let's try one of those. So the example I want to show you here is what we call an Atwood machine. And all an Atwood is are two masses attached with a rope, suspended on a pulley. They could be on a table. As long as those two masses are connected together, what we can do is write a system of equations to solve for the acceleration of the system. Let's call this mass 1. We'll call this mass 2. And just from the drawing, I can see that mass 1 is smaller than mass 2. What I can assume is that mass 1 will accelerate upwards, while mass 2 will accelerate downwards. If I want to identify the forces acting on each object, we can say, okay, the force of gravity is acting on mass 2. This rope must be pulling up with a tension to support mass 2. Over here, gravity is also acting on mass 1, not as much because mass 1 is not as big. And then there's tension, keeping mass 1 from falling to the ground. What we want to do here is write an equation for each mass individually and look at the accelerations of each mass separately. For mass 2 is accelerating negatively, and mass 1 is accelerating positively. Be careful with your signs. If you mess up a sign, your answer will be off, and that's probably where you're going to have your issues. So let's set this one up together. Force of gravity 1, force of gravity 2. We'll focus on mass 1 first. For mass 1, if I was going to write the forces, I would say T is my tension, pulls upward. The force of gravity pulls down on mass 1, so I'm just going to call it M1G. And what that does, that's my net force on the first mass. That's going to make mass 1 accelerate. So T minus M1G will equal M1A. If I look at mass 2 also has a tension on it. That tension is also up. It has gravity on it in the value of M2G. And what that's doing is making mass 2 accelerate. However, we need to show that mass 2 is accelerating downwards. So that's where that extra minus sign comes in. That's where things can go wrong for you. Don't mess up the signs, and you should be okay. So I could probably give you mass 1 and mass 2. The question is, what is the acceleration of this system? That's the overall goal. I want to solve for A. The nice thing is, this acceleration of mass 1 will match the acceleration of mass 2. They have to. They're attached, they're a tied system together. And in this case, as long as there's no slipping or friction with the pulley, we can assume that the tension on rope 1 goes all the way up and over the pulley and acts as the tension on rope 2. So really, I have two equations here with two unknowns. And we've seen this multiple times now. So what we're going to do is set some values equal to each other. If I want to solve for the acceleration, put the tensions equal to each other. And what that will give you is I'll solve T1, or I'll solve for the top one. That'll give me M1A plus M1G. And I'm going to take that and plug it into my second equation. So I'll get M1A plus M1G minus M2G equals minus M2A. So what I'd like to do here is get all the accelerations together. Get all the A's on the same side. So I want this acceleration and this acceleration to be on the same side. Is M1A plus M2A equals M2G minus M1G. So make sure that my signs are all correct. Go through that. Make sure I did everything fine. If you look on the acceleration side, I have M1 plus M2A I can factor out an a for acceleration and leave behind an m1 plus m2. And on the other side, I still have m2g minus m1g. If I want to solve for a, I just need to take m2g minus m1g and divide by m1 plus m2. So this will work for any scenario in an Atwood machine where you have two masses, one mass bigger than the other, and trying to determine the total acceleration of the system here. In this case, you can see that the force of gravity of m2 must be bigger than the force of gravity of m1. That being said, that means you have a net force. You have a net force on the top, all divided by total mass. And that really is the definition of acceleration. It's the total force over the total mass of the entire system that you're dealing with. If you're dealing with one object, you're only dealing with one mass. But in this case, we're dealing with multi-body systems, so you have two objects you have to worry about. Another thing that was brought up in some of the conceptual questions was this idea: if you're inside a plane or inside, I think, a limousine, they want to know, could you determine if you were accelerating? If the object is not accelerating, what you'd say is that there's a downward force of gravity on it, there's an upward force of tension, and those two must be equal. Since the forces are balanced, we're not accelerating, so the tension must equal mg. However, when you start to accelerate, the ball's inertia will say, try to keep doing what you were last doing. So when you accelerate forward, the ball will actually move back towards you. And when it moves back towards you, you can measure that angle, and you can see the force diagram up here. You have tension at an angle, and the force of gravity straight down. Looking at that, they're giving you a total net force of ma forward. And if you wanted to break this into components here, what you can see is there is a y component to the tension and an x component to the tension. The y component would equal your gravity, and the x component is what actually makes you accelerate. You could write tension in the x equals ma. So you could solve for the acceleration of the system, even though you weren't outside the system. You could solve for being inside. You could solve for it as if you were inside the system and just measuring how this pendulum moves. If you were cruising along, it would go right back to balanced forces again. And when you slam the brakes, you would see the pendulum swing away from you. That's because the pendulum was in motion. It wants to continue to stay in motion. And the last scenario I'll set up for you here is this. We've got three masses, all attached with ropes and pulleys. So in this scenario, what you want to do is, again, write a free body diagram for each one. And you can say that there's tension up on this block. We could say there's m3g over here. That's the force of gravity on block 3. Force of gravity on block 2, and the normal force on block 2. Those two, I'm going to assume, are equal since the block's not going to fall through the surface. And over here I've got m1g and tension. One thing I did forget on m2 is that there's tension both directions. I'll call this T3 for tension on block 3, and I'll call this T1 in that direction for the tension on block 1. So I've got lots of forces. I see many, many arrows here. What you want to do is focus on each object and make sure that you account for all the forces individually. I'm going to take away that gravity and the normal force there because looking at the system, it looks like block 3 is bigger than the rest, so the whole system is going to accelerate in that direction. So I'm going to call the direction with the arrow positive and write my equations for each. So for block 3, I have T3 up minus M3G down makes M3 accelerate downwards. For block 2, it's being tugged on by T3 to the right and T1 to the left, but that makes M2 accelerate to the right. And then for the last one, I've got T1 minus M1G makes m1a accelerate upwards. So now I've got three equations with three unknowns. But I want to solve for the acceleration of the system. So I'm going to solve for the tension in block 1, the tension in block 3, and just substitute those into that middle equation and get one gigantic force formula for all. So combining everybody, this is what the final equation comes to. M3G minus M3A minus M1A minus M1G equals M2A. Just like I did before, I'm going to combine all my masses and accelerations on one side and my mg's on the other. And what I'm left with is that the acceleration of the system here is the force of gravity on block 3 fighting the force of gravity on block 1. Block 3 is greater, so it's going to win. And we're going to divide that by the total mass of the entire system. Everybody is moving in the system. So when you start putting numbers in and values, your accelerations, the max they could ever get, let's assume that mass 1 breaks away. Let's say we cut this rope right here. What that's going to eliminate is block 2 from the system, and if I just focus on block 3, what disappears is T3. And if I go back to my equation, that means that in my equation here, M1G goes away, M2 and M1 are not accelerating because of block 3 anymore, and what we see is that the acceleration becomes G. The maximum anything can accelerate in a system on Earth is gravity. It cannot accelerate faster than 9.8 meters per second squared. If it is, you did something wrong. So any scenario when you have connected bodies in Atwood type problems, your acceleration should always be some type of fraction of the acceleration due to gravity. Half, 3/4, heck, it could even be A equals G. But that just means the whole system now is in free fall. Watch your signs. That's the biggest mistake people run into.